close this. All right, so let's start today's lecture. So this is a nice class in the sense that it's not something you have to take, right, to get to graduate. So usually people who come to this class 1690, at least they have some interest in math, right? So I think it's not inappropriate to start today's lecture with Euler's formula. I mean, Euler's formula is this very special formula that's very concise. So just in case you don't know or know it of a different name, it's e to the I pi plus 1 equal to what? 0, right? So this is in math, this is something super nice because it's so compact. And every single thing in this formula is special. I mean, none of them are just a number, right? Everything has its very deep meaning. Starting from 0. 0 is this special thing that has a link to the concept of addition. I mean, it's the only number that adds to itself is actually itself, right? 0 plus 0 is 0. It adds with anything else is 0. How about 1? 1 is this special number linked to multiplication, right? I mean, it's the only number that multiplies with anything is going to be itself, right? I is this special number that is linked to the concept of complex numbers and imaginary numbers, right? Its square is -1. And pi is this special number in geometry where it's the ratio of the circumference to the diameter. How about e? Right? What is the special thing about e? I mean, what does e mean to you? Why do we have a letter for that number? Yes?
Significant to calculus because the derivative of e to the x is itself.
Exactly. I mean, e is this actually special number to calculus. It's the only number if you use this as the base of exponential, right? The derivative is actually itself. In particular, a special case for that statement is that the derivative of e to the x when x is equal to 0 is 1, right? I mean, it's the only number. So basically, e to the x, the ddx of this number is equal to 1, right? So the exponential function, right? I mean, it's the solution. So that's why when we solve a differential equation, let's say we solve any differential equation, du dt equal to let's say any au, the solution is always e to the at, right? That's the solution. Okay, so this is basically the special place of e, right? So today let's try to use forward Euler to prove Euler's formula. How do we do that? Let's just use the property that e to the at, right, is a solution to the differential equation du dt equal to au. And in this case, let's set a equal to the imaginary number I. How about that? So basically, we'll look at this special equation. In particular, if a is equal to the imaginary number, then we have this special equation du dt equal to I times u. And if we integrate this equation using forward Euler for a time length equal to pi, what we should get is -1, right? Okay, so let's start doing that. And just to let you know, this is actually a valid approach to actually prove Euler's formula, is to actually look at the Euler's formula as a solution to this particular ordinary differential equation and go ahead and basically prove using geometric ways that the solution is going to be basically equal to -1 when t is equal to pi.